Spiral galaxies are cosmic loners no more. Those majestic whirlpools of stars, separated by billions of light years, are secretly linked in ways that defy our basic understanding of space. This journey will reveal a universe woven together by invisible threads of dark matter and cosmic evolution, fundamentally reshaping your perception of reality. How can a galaxy's rotation betray the presence of a hidden substance that permeates all of space? Why do the magnetic fields of distant spirals seem to whisper to each other across the void? By the end, you will see the night sky not as a collection of isolated islands, but as a single, interconnected web. What does it mean for our own place in the cosmos if every spiral is part of a grand, unified design? The universe has a skeleton, an invisible framework stretching across the emptiness. Picture a spider web on a dewy morning, glistening with countless droplets. Each of those dewdrops is a galaxy, and the silken threads holding them in place are filaments of dark matter. This is the cosmic web, the hidden architecture of everything. It is not a random scatter, but a carefully structured network where everything has its place. Astronomer J. Richard Gott called this the skeleton of the universe, a perfect description for the structure that dictates where galaxies will form and how they will grow. Our own Milky Way did not simply appear in a random patch of darkness. It was born at a cosmic crossroads, a dense intersection where several of these dark matter filaments met and intertwined. This privileged position provided a rich flow of gas, the raw material for building stars. The gravitational pull from these web filaments gently herds this gas, triggering the birth of new stars and sculpting them into those magnificent, sweeping arms that define a spiral galaxy. This process is not unique to us. Billions of light years away, another spiral galaxy is experiencing the same cosmic nurture, guided by the same invisible hand. They are siblings in structure, not through direct contact, but because they both grew within the same vast, nurturing web. Their shared form is a testament to a shared origin story written in the language of gravity and dark matter. So the next time you see an image of a lone spiral galaxy, remember it is not truly alone. It is suspended in a cosmic cradle, its beautiful shape a direct reflection of the hidden architecture that holds it. Those majestic spiral arms, visible across billions of light years, present a profound mystery. How can galaxies separated by an unthinkable void all choose the same breathtaking design? It is as if a single, fundamental rhythm is pulsing through the cosmos, and every spiral galaxy is dancing to its beat. The answer may lie not in a static structure, but in a moving pattern. Think of a traffic jam on a vast celestial highway. The cars themselves are the stars and gas clouds moving along their orbits. The traffic jam, however, is a pattern that moves independently, a region of compression where everything slows down and piles up. This is the essence of density wave theory, a concept developed by astronomers C. Lin and Frank Hsu. In a galaxy, this dense wave rolls through the disk, squeezing interstellar gas. This compression triggers the birth of brilliant, short-lived stars, which illuminate the wave crest just like cars packed tightly together in that traffic jam. The spiral arms we see are not permanent fixtures made of the same stars, but a pattern of star formation, a dynamic and ever-changing process. The universal physics of gravity and rotation ensure this process unfolds in a similar way from one galaxy to the next. Yet there is more to the story. These graceful patterns might also be seeded and sustained by gentle nudges from the cosmic web itself, or by minor mergers with smaller galaxies. These interactions provide the initial push that sets the spiral rhythm in motion. So when we see the grand design of a nearby galaxy like NGC 1300, and then spot its nearly identical twin on the far edge of our vision, we are not just seeing a coincidence. We are witnessing a signature. It is the signature of a fundamental blueprint for beauty, a cosmic law of form that dictates how a swirling disk of stars will inevitably organize itself. This leads to an even deeper question. If the form is universal, what about the content within that form? Could the very stars themselves also be part of a shared cosmic heritage? But the spiral's elegant form hides a deeper cosmic defiance. Every one of these galaxies, from our nearest neighbor Andromeda to the faintest whirlpool at the edge of our vision, spins in a way that should be impossible. According to the established laws of gravity, stars on the outer fringes of a spiral should move much slower than those near the bright core, just as the distant planets in our own solar system plod along in their orbits compared to the inner worlds. Yet when astronomer Vera Rubin measured these galactic rotations, she found something astonishing. The stars at the very edge race along at virtually the same speed as those near the center. It is as if the entire galaxy is a solid disk, spinning as one. This discovery, the flat rotation curve, shattered expectations. The only plausible explanation was that each galaxy is embedded within a massive, invisible sphere of something that does not emit or reflect light, a substance we now call dark matter. This hidden halo provides the extra gravitational grip to whip the outer stars around at such incredible speeds. The true revelation, however, is not just that dark matter exists, but that its recipe is universal. The rotation curves of spiral galaxies are hauntingly similar, regardless of their size, age, or distance from us. This implies a cosmic constant, a fixed ratio of dark matter to the ordinary, star-filled matter we can see. Every spiral galaxy, across billions of light-years, is built using the same hidden blueprint. Their consistent spin is a direct result of this shared, invisible ingredient. This suggests that the dark matter halos enveloping these galaxies are not truly isolated. They are the densest knots in the vast, interconnected cosmic web, all part of a single, pervasive system. The uniform rotation we observe is a ghostly signature, a synchronized dance dictated by this great cosmic connector. So when we measure the spin of a distant spiral, we are not just studying one galaxy. We are reading a message about the fundamental, hidden architecture of the entire universe, an architecture that connects every single one of these celestial whirlpools through the silent, gravitational influence of dark matter. This silent dance of dark matter and stars is not the only connection echoing through the void. Far from being empty, the space within a spiral galaxy is threaded with immense, invisible forces. We are now discovering that these forces, these magnetic fields, are themselves part of a grand synchronization. Recent observations from powerful radio telescopes have uncovered a startling secret. The magnetic fields within spiral galaxies do not wander randomly. They often align perfectly with the majestic spiral arms, tracing their curves like an unseen artist sketching over the visible light. In some cases, this magnetic order stretches even further, showing coherence across vast intergalactic distances. It is as if we are seeing the faint outline of a cosmic blueprint, one written in the language of magnetism. How could such an intricate pattern arise in places so far apart they have never directly touched? The answer may lie in the very birth of the universe. Theorists suggest these magnetic fields were seeded in the primordial cosmos, imprinted in the fabric of space-time during its first moments. Then, as the universe expanded and galaxies began to spin, these faint seed fields were stretched, twisted, and dramatically amplified. This process is known as dynamo theory. Picture a simple bicycle dynamo. The turning of the wheel spins a magnet, generating an electrical current that powers the light. A galaxy operates on a similar, but vastly more powerful, principle. The immense rotational energy of the entire spiral galaxy acts like that spinning wheel, converting motion into magnetic energy and strengthening the initial seed field over billions of years. Because the fundamental physics of rotation and plasma are universal, this process naturally builds magnetic fields with similar architectures, even in galaxies isolated from one another. These invisible fields are far from passive. They shape the very life cycle of a galaxy. They can guide the collapse of giant gas clouds, nudging star formation into the spiral arms. They influence the paths of high-energy cosmic rays, acting as a vast interstellar guidance system. The discovery that galaxies billions of light-years apart possess magnetic fields following similar patterns is a profound clue. It implies a shared origin, a universal physical law that governed the birth of magnetism itself. This magnetic connectivity weaves another hidden thread between the spirals, a silent, forceful whisper that hints at the primordial order imprinted on our cosmos at the very beginning. Yet another silent law governs the spiral galaxy, one written not in light or motion, but in the very chemistry of its stars. If you could take a core sample from the heart of a spiral galaxy and analyze it like a cosmic geologist, you would uncover a distinct chemical pattern. The galactic center is rich with metals, the complex elements forged in stellar furnaces, but as you travel outward, this metal content steadily declines. This is the Metallicity Gradient, a universal fingerprint found in every spiral we can study. It is a fossil record of the galaxy's own life story. The reason for this pattern points to a specific kind of birth. Galaxies appear to form from the inside out. The densest core collapses first, triggering a frenzy of star formation. These first generations of stars live fast and die young, exploding as supernova and seeding the inner regions with the heavy elements they created. This enriched gas then fuels the next wave of star building, creating a metal-rich core. Meanwhile, the outer regions are still slowly gathering their gas, a pristine material that has not been through this cycle of stellar life and death. When stars finally form in these outer suburbs, they are born from poorer stuff, resulting in that smooth decline in metals we observe. The profound part is not that this happens in one galaxy, but that we see the same chemical story playing out in spirals separated by unimaginable distances. This tells us that the fundamental physics of star formation, stellar death, and gas recycling operate with the same clockwork precision across the cosmos. The timescales and efficiencies of this grand cycle are not random. They are dictated by universal laws, a shared recipe that every spiral galaxy follows. This chemical consistency also hints at a uniform starting point. The primordial gas clouds that collapsed to form these galaxies must have had very similar properties, or that powerful feedback processes, like the violent winds from supernova, regulate the distribution of metals in a predictable way, scrubbing the inner galaxy and pushing pristine gas to the outskirts. By reading these subtle chemical gradients, astronomers are deciphering a shared historical narrative. It is as if every spiral galaxy, from our local neighborhood to the farthest reaches of space, read the same cosmic instruction manual for how to grow up. This common path of chemical evolution is one of the strongest hints that these majestic structures are not just similar in shape, but are deeply connected in their very origins and life cycles. But the connections do not stop at the galaxy's edge. Look further out into the vast halo of darkness surrounding a spiral like our own Milky Way. Here, a troop of smaller satellite galaxies orbits the central giant. For a long time, it was assumed this entourage would be a chaotic swarm, a random scattering of captured dwarfs. Yet the reality is far more structured. These satellites are not randomly distributed. Instead, they tend to move within a startlingly thin, flattened plane, a disk that is often aligned with the majestic spiral of their host. We see this in our own galactic neighborhood and in our great spiral neighbor, Andromeda. This is not what standard models predicted. If these small galaxies were simply captured over time, their orbits should point in every direction, forming a loose spherical cloud. The fact that they are so neatly arranged suggests a deeper coordination. It is as if the entire system, the Great Spiral and its tiny companions, all formed from the same spinning cradle of gas and dark matter long ago. The host galaxy's immense dark matter halo, which itself has a preferred orientation, could be guiding these satellites into their orderly paths, or perhaps the influence comes from an even larger scale. The same cosmic web filaments that gave birth to the central spiral may also be funneling these smaller systems into place, directing their infall along set intergalactic highways. This persistent alignment across different galaxies is a powerful clue. It implies a common formation mechanism, a universal rule for how galactic families are assembled. The coordinated dance of these satellite systems acts like a cosmic fingerprint, uniquely linking each spiral galaxy to its specific environment and history. Unraveling this riddle reveals more than just the fate of a few small galaxies. It shows us how the cosmos orchestrates motion on a grand scale, ensuring that even the smallest dancers are part of the same magnificent ballet. The spiral's grand design holds another common secret deep within its core. Many of these cosmic whirlpools, our own Milky Way included, are not simple pinwheels. They are barred spirals, featuring a bright, elongated structure of stars cutting directly through their center. This is not a rare fluke. A staggering number of spirals, observed across vast stretches of space and time, share this exact same architectural feature. Why would galaxies separated by billions of light-years repeatedly choose to build this same central bar? The answer seems to lie in the inherent instability of a spinning disk of stars. Left to its own devices, a galactic disk can naturally develop a wobble, a gravitational ripple that eventually pulls stars into that elongated, bar-shaped orbit. It is a predictable outcome of celestial mechanics, like a spinning coin finally settling onto a table, but the sheer commonality of these bars suggests something more is at work. Perhaps these instabilities are not entirely random. They could be gently nudged into existence by the subtle gravitational tides of the cosmic web, or triggered by a minor merger with a small, companion galaxy. These events are cosmic constants, happening everywhere throughout the universe's history, providing a universal trigger for a universal shape. Once a bar forms, it becomes a powerful engine for change. It acts like a giant cosmic whisk, churning the galaxy's inner regions and funneling vast rivers of gas inward toward the core. This influx of fresh fuel can trigger intense bursts of star formation and even feed the supermassive black hole lurking at the very center, lighting it up as a brilliant active galactic nucleus. The bar, therefore, is a self-regulating mechanism. It dictates the pace of a galaxy's evolution, controlling how it uses its remaining gas reserves. The most profound clue is that we see barred spirals at extremely high redshifts, meaning we are observing them as they were billions of years ago. This tells us the process is not a modern development. It began early and has been a recurring theme in the life story of spiral galaxies. The widespread presence of these stellar bars connects them through a shared developmental phase. It hints at a predictable, almost inevitable, pathway in their life cycles. If a spiral galaxy has a stable, massive disk and enough time to rotate, the formation of a bar seems to be a natural step in its maturation. This commonality is a powerful signature, one more thread tying these distant island universes together through a shared evolutionary script written in the language of gravity and motion. The elegance of a spiral galaxy holds one final, profound secret. Its brilliance is not random. The intrinsic luminosity of a spiral, the total light from its billions of stars, is locked in a perfect dance with its speed. This is the Tully-Fisher Relation, a discovery by astronomers R. Brent Tully and J. Richard Fisher that reveals a hidden cosmic harmony. The faster a spiral galaxy rotates, the brighter it shines. This is not a loose trend but a precise mathematical relationship, a rule that holds for thousands of galaxies across the observable universe. How can something as simple as a galaxy's spin so accurately predict its total stellar output? The answer lies in the invisible hand of dark matter. A galaxy's rotation speed is dictated by the mass of its dark matter halo, the immense, unseen sphere of material that grips the entire system. A more massive halo spins faster, and crucially, it gathered more primordial gas during the galaxy's formation. More raw gas means more fuel for star formation, which ultimately leads to a brighter galaxy. This creates a direct chain of cause and effect, linking the hidden dark matter to the visible light we observe. This relationship is so reliable that astronomers use it as a cosmic measuring tape. By simply measuring how fast a distant spiral rotates, we can deduce its true brightness and calculate its distance from us across billions of light years. The true wonder, however, is its universality. From a nearby spiral like Messier 33 to the faintest whirlpools at the edge of our telescope's vision, the Tully-Fisher relation holds firm. This tells us something astounding about the process of galaxy birth. The way gas collapses, cools, and turns into stars within the gravitational confines of a dark matter halo is not a chaotic free-for-all. It is a regulated, predictable process that follows the same cosmic recipe everywhere. The diversity we see in spiral galaxies is merely a variation on a theme, all governed by this one simple law. The Tully-Fisher relation is perhaps the ultimate evidence that these majestic structures are not isolated works of art. They are products of a single, universal set of physical laws, each one a unique expression of a common, underlying order written into the fabric of space and time. This coordination is galactic peer pressure on a cosmic scale. Why would a central galaxy's burst of star formation influence its neighbors millions of light years away? They are not close enough to be gravitationally bound, yet their behaviors are mysteriously synchronized. This is the phenomenon of galactic conformity, a discovery that shatters the old idea of galaxies as isolated islands. It is as if an entire galactic neighborhood receives the same memo, a silent signal that orchestrates their growth cycles in unison. The most likely messenger is the cosmic web itself. Picture a single vast filament of dark matter, a river of invisible material flowing through the void. Along this filament, galaxies form like beads on a string, all drawing from the same primordial reservoir of gas. If a wave of energy sweeps through this filament, perhaps from a colossal supernova explosion in the central galaxy, it could trigger a chain reaction. This wave might gently compress the gas clouds in all the neighboring galaxies, nudging them into a simultaneous burst of star formation. Alternatively, the shared history might be written even earlier. The entire region could have been pre-enriched by the first generations of stars, seeding the gas with the heavy elements necessary for future star birth. When the conditions are right, this common foundation causes all the galaxies in the volume to awaken at the same time. This conformity reveals a universe where influence extends far beyond the visible edges of a galaxy. The diffuse, superheated gas that fills the space between galaxies, along with the overarching dark matter scaffold, acts as a communication network. It carries the imprint of past events and regulates the future growth of everything within its domain. The destinies of these spirals are not their own. They are woven together by the environment they all share, a reminder that even across the deepest voids, no galaxy is truly an island. This mathematical harmony extends far beyond a single law. The elegant dance of the Tully-Fisher relation is just one movement in a grander symphony of scaling laws that govern every spiral galaxy. If you know a galaxy's mass, you can predict its size. If you know its rotational velocity, you can deduce its luminosity. These properties are not independent. They are locked together in precise, predictable relationships that hold true from our cosmic backyard to the farthest reaches of observable space. This is not a mere coincidence. It is a direct consequence of the universal physics that presided over their birth. Every spiral galaxy began as a spinning cloud of primordial gas, collapsing under its own gravity. A fundamental rule of physics, the conservation of angular momentum, dictated that as this cloud shrank, it had to spin faster, just like an ice skater pulling in their arms. This initial spin prevented the cloud from collapsing into a simple sphere, instead flattening it into the iconic disk we recognize today. The final size and rotation of that disk were set in stone billions of years ago by the amount of spin its primordial cloud possessed. The dark matter halo plays its part too, acting as a gravitational mold that dictates how much gas can be gathered and how fast the resulting galaxy will ultimately spin. The stunning consistency of these scaling relations across cosmic time is a powerful clue. It tells us the recipe for building a spiral galaxy has not changed. The same processes of gravitational collapse and angular momentum conservation that shaped the earliest galaxies are still at work today, operating with clockwork precision. This hidden mathematical order connects all spirals as if they were different-sized expressions of the same underlying equation. Why does this universe, in all its apparent chaos, choose such exquisite mathematical regularity? The answer may be written in the very first moments of time, in the initial conditions that seeded the cosmic web with a specific, reproducible set of physical parameters. Discovering these fundamental constants is like finding the signature of the cosmos itself, a signature repeated in the beautiful, predictable form of every spiral galaxy we see. Peering deeper into a spiral's structure reveals a hidden layer, a ghostly halo of ancient stars enveloping the bright disk. This is the thick disk, a population of older, faster-moving stars that extends high above and below the galaxy's main plane. Our own Milky Way has one, and so do countless other spirals across the universe. Its widespread presence is a profound clue, a fossil record of a galaxy's turbulent youth. How did these stars get flung so far from the orderly plane? One compelling theory points to a violent early chapter. In the first few billion years after the Big Bang, the universe was a much more crowded and chaotic place. Young galaxies frequently collided and merged with smaller neighbors. Each of these merger events would have violently shaken the stellar disk, scattering stars into a puffier, thicker configuration. If this is the primary cause, then every thick disk we see is a lasting scar, a monument to ancient collisions that most spiral galaxies endured in their formative years. This would mean that the serene spiral we observe today is the calm after a long-forgotten storm. An alternative explanation suggests a more internal, gradual process. Over vast stretches of time, the collective gravitational pull of giant molecular clouds or recurring instabilities within the disk itself could gently nudge stars, providing a steady heating that slowly puffs the disk up from within. This process, known as dynamical heating, might occur naturally in any mature spiral. The very fact that thick disks are so common suggests that the mechanisms which create them, whether violent mergers or internal heating, are universal ingredients in the recipe for a spiral galaxy. They are a shared architectural feature, a hidden thread connecting the present-day calm of a spiral to its tumultuous past. By studying the chemical composition and motions of these ancient thick disk stars, astronomers can perform a kind of galactic archaeology. They are reading the life story of a galaxy, written in the orbits of its oldest inhabitants. The consistent properties of thick disks from one galaxy to another tell us that the early universe was a place of both great violence and remarkable order, where the same fundamental processes shaped these majestic structures, linking them across time and space through a common developmental history. These faint stellar streams are the ghosts of ancient meals, Wrapping around spiral galaxies like our own, they are the final, dissolving evidence of smaller galaxies that were pulled in and torn apart by immense gravitational forces. This is not a unique story for the Milky Way. Deep observations of other nearby spirals reveal the same haunting features: faint rivers of stars flowing through their dark halos. The Sagittarius stream encircling our galaxy is just one local example of a universal phenomenon. The sheer prevalence of these streams tells a powerful story, one of hierarchical assembly. It seems the cosmos has a preferred method for building its largest structures. Giant spiral galaxies do not simply form in isolation. They grow over billions of years by consuming smaller neighbors, a process of cosmic assimilation that is written in the sky for those who know how to look. The patterns of these streams are not random. They are celestial archives. The specific shape and path of a stellar stream encode the history of the original dwarf galaxy and the detailed properties of the massive dark matter halo that shredded it. The fact that we observe such similar stream structures in different galaxies sends a profound message. It suggests that the population of small, satellite galaxies must be comparable from one spiral to the next, and the fundamental physics of tidal disruption, the process of being pulled apart by gravity, operates with the same clockwork precision everywhere. These stellar fossils provide a direct link to a violent, shared past. They show that the majestic, tranquil spirals we see today are the products of a consistent and ruthless growth process. By learning to read these faint stellar currents, astronomers can uncover a common narrative. It is a story of galactic cannibalism, a shared history of growth by assimilation that intimately connects every massive spiral through the same developmental crucible. This violent past is, ironically, one of the strongest threads tying their present forms together. This universal blueprint for stars is perhaps the most silent and profound connection of all. Deep within the swirling gas of any spiral galaxy, from our own to the farthest we can observe, lies a hidden rule governing the very first moments of a star's life. It is called the initial mass function, and it dictates a simple but astonishing fact. Whenever a giant cloud of gas collapses to form a cluster of new stars, the resulting family of stars will have a remarkably similar mix. For every single brilliant, high-mass star that blazes into existence, there will be a predictable number of smaller, dimmer, sun-like stars, and a vast multitude of faint red dwarf stars. This cosmic census is not random. It is a consistent ratio repeated across the universe. This means the stellar nursery in a distant spiral arm, billions of light years away, is producing stars with the same distribution of masses as the Orion Nebula in our own cosmic backyard. The implications are staggering. The initial mass function is the master architect for a galaxy's entire life cycle. High-mass stars are the cosmic powerhouses. They live fast, explode violently, and seed the galaxy with heavy elements. The more common low-mass stars burn for trillions of years, providing long-term stability. Because this stellar recipe is universal, the fundamental processes of lighting up a galaxy and enriching it with the elements for planets and life are governed by the same rules everywhere. The reason for this consistency points to the bedrock laws of physics. The chaotic turbulence within a gas cloud, the relentless pull of gravity, and the fundamental rules of thermodynamics appear to interact in a single, predictable way to fragment a cloud into clumps that become stars. It seems the cosmos has a preferred method for building stars, a method that depends only on these universal constants, not on the specific location or history of the galaxy. This is why astronomers can look at the integrated light of a galaxy so far away its individual stars are invisible, and still confidently deduce the history of its star formation. They know, with remarkable certainty, the basic makeup of its stellar population. The universal initial mass function is a silent promise of cosmic order. It assures us that the building blocks of reality, the stars themselves, are forged from the same fundamental mold, connecting every spiral in the universe through a shared stellar DNA. The universe has painted its galaxies in two fundamental colors. When astronomers map the cosmos, they find a striking division, a great bimodality that separates the population into a vibrant blue cloud and a dormant red sequence. Spiral galaxies, almost without exception, belong to the blue cloud. This is not a simple aesthetic choice. The blue hue is the signature of youth, a brilliant glow from countless newborn, massive stars. Their light is so intense it drowns out the redder glow of older stellar populations. Elliptical galaxies, by contrast, reside on the red sequence, their star-forming fuel long since depleted or expelled, leaving behind a cooler, aging stellar populace. This color split is not a local phenomenon. It is a universal feature observed in galaxy surveys spanning billions of light years. The hidden connection is that spiral galaxies, regardless of their individual histories, share a common cosmic destiny of prolonged star formation. They are the universe's great incubators, consistently maintaining their vibrant blue hue across eons. What universal mechanism allows them to remain in this state of active creation for so long, while other galaxy types grow red and quiet? The answer appears woven into their very structure. The stable, rotating disk of a spiral galaxy is a perfect cradle for star birth. It allows vast reservoirs of cold gas to settle and remain undisturbed, protected from the violent shocks that can heat or strip gas in more chaotic galactic environments. Furthermore, the cosmic web provides a continuous, gentle rain. Spiral galaxies, positioned at the intersections of dark matter filaments, are efficient at siphoning fresh, pristine hydrogen from the intergalactic medium. This constant accretion replenishes the fuel for new stars, counteracting the natural consumption and loss that would otherwise lead to quenching. This shared reliance on a universal gas supply and a protective disk structure links the fate of every spiral. Their persistent place in the blue cloud is a testament to a common life path, one of sustained creation. Yet this very stability contains the seeds of its own end. The same processes that feed the blue cloud can, under the right conditions, trigger the transition to the red sequence. This great color division is far more than a simple classification. It is a dynamic map of galactic life and death, a universal pattern that intimately connects the evolutionary story of every spiral galaxy in the cosmos. Even the most perfect spiral is not immune to a subtle cosmic bend. Look closely at the outer edges of a galaxy like our own Milky Way, and you will discover its disk is not perfectly flat. It twists upward on one side and downward on the other, like a vast, slow-motion wave frozen in starlight. This is the galactic warp, a common yet mysterious distortion found in a majority of spiral galaxies. Its very existence reveals that these grand structures are not rigid platters, but flexible, dynamic membranes, constantly responding to the unseen forces that surround them. Where does this gentle bending come from? One of the prime suspects is the gravitational pull of satellite galaxies. As these smaller systems orbit their massive host, their persistent tidal tug can gradually torque the outer disk, where the gravitational grip of the central galaxy is weakest. It is a cosmic dance where the smallest partner can, over immense timescales, lead the largest. Yet there is another, more hidden possibility. The immense dark matter halo that cradles the galaxy may not be perfectly aligned with the disk of stars. If this invisible sphere is even slightly lopsided or tilted, its pervasive gravity will continually pull on the disk, trying to twist it into a new orientation. The prevalence of these warps tells us that such misalignments or external nudges are not rare events. They are a standard part of the galactic environment, a common experience for spirals everywhere. The fact that we observe similar warped structures in galaxies both near and far, some as they appeared billions of years ago, is a profound clue. It means the physical processes that create these bends are universal constants, as fundamental to a galaxy's life as the formation of its spiral arms. These warps connect spiral galaxies through a shared susceptibility, a universal flexibility in the face of gravitational influence. They are a testament to an ongoing, dynamic conversation between a galaxy and its environment. By studying the specific shape and motion of a warp, astronomers can perform a unique kind of cartography. They are not just mapping the visible stars, but charting the invisible gravitational landscape, tracing the pulls and pushes of both nearby companions and the great, dark halo that holds it all together. This subtle bending of starlight is, therefore, a powerful diagnostic tool, a visible signature of the invisible forces that continually sculpt our universe. This faint chemical whisper drifting through the void is perhaps the most intimate connection of all. The space between galaxies is not a perfect vacuum. It is filled with a superheated, incredibly thin gas known as the intergalactic medium. For a long time, it was assumed this vast expanse was primordial, a pristine relic of the early universe composed only of hydrogen and helium. But modern telescopes have detected a startling signature within it, the faint trace of heavier elements like oxygen, carbon, and iron. We call these elements metals, and their presence in the intergalactic medium is a profound puzzle. How did these metals, which can only be forged in the hearts of stars and scattered by their violent deaths, end up polluting the deepest voids? The answer lies in the explosive youth of spiral galaxies themselves. Billions of years ago, when the first generations of massive stars lit up within these young spirals, they lived short, brilliant lives before erupting as supernova. These cataclysmic explosions did more than just seed their own galaxies with metals. They generated immense, powerful winds that blasted right through the galactic boundaries, hurling these newly forged elements far out into intergalactic space. This process, galactic feedback, was a form of cosmic pollution on an unimaginable scale. The truly revealing part is the pattern of this pollution. The metallicity of the intergalactic medium is not random. In the vast regions surrounding spiral galaxies, the distribution of these heavy elements is surprisingly uniform. This consistency is a fossilized echo of that early frenzy of star formation. It tells us that the efficiency of this feedback process, the ability of a young galaxy to expel its enriched gas, was remarkably similar from one spiral to the next. The violence of stellar birth and death was not a chaotic free-for-all, but a regulated, universal phenomenon. This means the very gas that floats in the immense spaces between galaxies, the raw material that might one day collapse to form a new generation of stars in a new spiral disk, is not pristine. It carries within it the chemical imprint of countless ancestral galaxies. We are witnessing a cosmic recycling system of breathtaking scope. The iron in your blood, the oxygen you breathe, were not only forged in a star within our own galaxy. Their identical atoms were likely scattered long ago from a spiral galaxy billions of light years away, traveling for eons through the intergalactic medium before becoming part of the cloud that gave birth to our Sun. This shared chemical heritage irrevocably links every spiral in the cosmos. Their collective outbursts in the distant past created the common environment they all now inhabit. The story of a single galaxy cannot be told in isolation, for its history is written in the enriched atmosphere of the entire universe, a permanent chemical bond connecting all celestial islands. The spiral arms themselves are a magnificent riddle. We understand they are patterns like traffic jams in starlight, but what first sets this cosmic rhythm in motion? The initial spark for these grand designs remains one of astronomy's deepest puzzles. We witness spiral patterns being clearly triggered by gravitational encounters. When two galaxies pass near one another, their mutual tidal pull can stretch and stir the stellar disks, often igniting the formation of spectacular spiral arms as a direct response to the interaction. Yet this cannot be the whole story. We observe countless majestic spirals floating in profound isolation, with no galactic neighbors for millions of light years. These lone whirlpools possess the same elegant, well-defined arms as their social counterparts. This presents a fascinating duality. It suggests the universe has multiple, universal pathways to achieve the same beautiful end. For some galaxies, the trigger is external, a gentle nudge from a passing giant. For others, the mechanism is entirely internal. The rotating disk of stars and gas itself may become gravitationally unstable. As it grows more massive, it can naturally develop waves and ripples, a sort of resonant frequency that organically blossoms into the spiral pattern we see. There is even the intriguing possibility that invisible dark matter substructure, smaller clumps within the galaxy's vast halo, could provide the subtle gravitational perturbations needed to seed the arms. The hidden connection lies in the universal physical conditions required for this to happen. Any rotating disk with sufficient mass and self-gravity possesses the potential to birth spiral arms. It is a fundamental mode of such a system, a natural way for it to settle into a stable yet dynamic state. The stunning similarity of spiral arms from one galaxy to the next, regardless of their trigger, tells us that the underlying physics of disk stability and wave propagation are universal constants. The mathematics of a spinning, self-gravitating fluid plays out with perfect fidelity across the cosmos. Whether the initial push comes from a galactic flyby or a whisper from within, the resulting spiral is a universal solution. It is the most efficient, the most natural, and the most beautiful way for a vast disk of stars to organize itself. This shared physical response intimately links every spiral galaxy, revealing that their iconic form is an inevitable and recurring verse in the cosmic song of motion and gravity. The violent death of a star is not a solitary event. When a supernova explodes within a spiral galaxy, it is part of a grand, cosmic metronome. The rate of these cataclysms ticks with a predictable rhythm, one that is directly tied to the galaxy's mass and its pace of star formation. This is not a loose correlation, but a precise law that governs stellar demise. A large, bustling spiral, rich with young stars, will host supernova frequently, while a quieter, smaller spiral will experience them only rarely. This universal clockwork reveals a profound connection. The life cycle of massive stars, from their turbulent birth in cold gas clouds to their final, brilliant demise, operates on a consistent timeline everywhere. The physics that dictates how long a star will burn its nuclear fuel before collapsing is a fundamental constant of nature, as reliable in a galaxy 10 billion light-years away as it is in our own. This means the entire sequence, from star formation to stellar death, is a packaged process with a fixed duration and a predictable outcome. The supernova rate is the final, explosive tick of this universal clock. This regularity transforms random stellar death into a coordinated, self-regulating system. The energy and newly forged elements blasted into space by these supernova are delivered in precise proportion to the galaxy's needs. A massive galaxy, forming many stars, receives a correspondingly large dose of feedback. This energy can heat surrounding gas, preventing it from collapsing to form new stars too quickly, or even drive powerful galactic winds. The heavy elements created in the blast, the iron for future planets and the oxygen for future atmospheres, are seeded back into the galaxy at a rate that matches its growth. This creates a beautiful balance, a feedback loop that prevents the galaxy from either exhausting its fuel in a single, furious burst or stagnating entirely. The supernova in a distant spiral are not isolated fireworks. They are part of a statistical symphony, a shared rhythm of birth and destruction that ensures the evolution of these majestic structures is not chaotic, but guided. By counting these stellar explosions across the universe, we are not just watching individual stars die. We are witnessing the steady, regulated heartbeat of galaxy evolution itself, a pulse that connects every spiral through the immutable laws that govern the lives and deaths of their most brilliant stars. This beautiful equilibrium is a cosmic balancing act. The stunning spiral disk you see in any galaxy image is a structure in constant, delicate negotiation between two powerful forces. On one hand, there is the relentless pull of gravity, which constantly tries to collapse the disk, fragmenting it into clumps. On the other, there is the supporting pressure from the gas itself and the sheer energy of its motion, which fights to keep the disk puffed up and stable. For a spiral to persist for billions of years, these forces must be perfectly balanced. Astronomers measure this balance with a specific number known as the tumor Q parameter. Think of it as a galaxy's vital sign, a single reading that tells you whether the disk is stable or on the verge of collapse. Remarkably, across the universe, this number tends to hover right around the same critical value. It is as if every spiral galaxy has an internal thermostat, constantly making small adjustments to keep itself in a state of marginal stability. This is not a coincidence. It is a self-regulating feedback loop, a universal mechanism written into the laws of physics. When a region of the disk becomes too unstable and begins to collapse, it triggers a burst of star formation. The most massive of these new stars live short, violent lives and explode as supernova. These explosions inject tremendous energy back into the surrounding gas, stirring it up, creating turbulence and effectively turning up the pressure. This renewed support pushes the stability parameter back into the safe zone, preventing a catastrophic chain reaction of collapse. The galaxy has effectively healed itself. This elegant dance between collapse and feedback ensures that spiral disks do not tear themselves apart or stagnate. They naturally evolve toward this preferred state of equilibrium, a sweet spot that allows for ongoing star formation while preserving the grand, rotating structure. The hidden connection is that this self-regulation works under a wide range of starting conditions. Whether a galaxy began with more or less gas, or a faster or slower spin, the physics of instability and turbulence guide it toward the same stable outcome. The majestic, flat disk of a spiral is therefore not a fragile accident. It is the most natural, robust, and universal state for a massive, rotating system to achieve. This shared stability criterion is a silent, dynamic thread that connects every spiral, ensuring their graceful forms can endure across the eons. Deep within the heart of so many spirals, a cosmic engine occasionally flares to life. The supermassive black hole at the center, normally quiet and dark, can ignite into an active galactic nucleus, blazing with the light of a billion stars. For a long time, these outbursts were thought to be random, isolated events, the internal struggles of individual galaxies, but a strange pattern has emerged from the darkness. In the densest neighborhoods of the universe, where galaxies cluster together along the same vast filaments of the cosmic web, these brilliant AGN do not flare up at random. They turn on and off in eerie synchrony, a flickering that seems coordinated across millions of light years. This phenomenon, called AGN clustering, suggests these cosmic engines are not independent. They are responding to the same large-scale environmental cues. The primary trigger for a black hole's feast is a supply of fresh gas. It appears that the cosmic web itself can orchestrate this delivery. When a vast river of intergalactic gas, flowing along a dark matter filament, encounters a cluster of galaxies, it can simultaneously fuel the central black holes in multiple systems. A collective triggering event, like the shockwave from a group of galaxies falling into a cluster, could also compress gas reservoirs across the entire neighborhood, nudging numerous black holes to awaken at once. The hidden connection here is profound. The growth of the most violent objects in the universe, the supermassive black holes, is not solely an internal affair. It can be directed by the architecture of the cosmos on its very largest scales. This Aegean conformity means that the evolution of a spiral galaxy is linked to its cosmic address. A galaxy residing at a busy filament intersection may experience repeated, synchronized bursts of activity from its core, dramatically influencing its star formation and overall development. The synchronized flickering of these brilliant beacons reveals a cosmos where influence flows seamlessly from the largest structures down to the most compact, energetic points. It shows us that even the destiny of a black hole is woven into the grand, interconnected tapestry of the cosmic web. Even the most stable spiral galaxy is a scene of constant upheaval. Supernova explosions do far more than just seed the galaxy with metals. They launch titanic fountains of hot gas high above the serene disk. This gas, heated to millions of degrees, surges upward into the galactic halo, forming vast, billowing clouds that glow faintly in X-ray light. But this journey does not end in the halo. As the gas travels, it radiates away its immense heat, cooling over millions of years until it condenses into dense, cold clumps. Then, pulled by the galaxy's relentless gravity, this material begins its long fall back down, raining onto the disk below in a celestial downpour. This is the galactic fountain, a continuous cycle of outflow and inflow that acts as the galaxy's own circulatory system. It is a form of cosmic respiration where the galaxy exhales its enriched breath, and then inhales it once more, purified and ready for reuse. This process is not a rare event. Observations suggest it is a standard feature in star-forming spirals across the universe. The very existence of these fountains reveals a delicate balance. The energy from stellar explosions must be powerful enough to lift the gas against the galaxy's gravity, but not so powerful that the gas escapes entirely into intergalactic space. The universality of this fountain flow means this balance is struck again and again, a natural equilibrium between stellar fury and gravitational pull. This creates a hidden connection, ensuring the gas within spiral galaxies is not stagnant. The fountain continuously mixes it, stirring the heavy elements from the inner regions out into the wider disk and halo. This churning action helps explain the surprisingly uniform metallicity we see in the gas clouds of many spirals, as the fountain works like a giant blender, homogenizing the galactic ingredients. This process intimately links the three major components of a galaxy: the star-forming disk, the extended halo, and even the intergalactic medium. It shows that a galaxy's evolution is an open system, not a closed one. Gas is not simply locked in place. It is in constant motion, cycling through different phases and regions. The fact that this same fountain model applies to small, isolated spirals and massive ones in crowded clusters points to a fundamental truth. This recycling is a core aspect of how any active, star-forming disk manages its energy and material. It is a shared metabolic process, a common mechanism of self-regulation that ensures these majestic structures can sustain their star-forming lives for billions of years. This galactic metabolism connects every spiral through a vital, invisible rhythm of expulsion and return, a breath held in common across the cosmos. This universal blueprint extends even to the darkness itself. The invisible halos of dark matter that cradle every spiral galaxy are not chaotic clouds. Instead, they follow a precise and hauntingly similar internal architecture, a specific gradient of density known as the Navarro-Frank white profile. From the smallest dwarf spirals to the largest cosmic whirlpools, the dark matter within them is arranged according to the same mathematical rule. This is a profound discovery, because these halos were not built by hand. They emerged over billions of years through a violent and chaotic process called hierarchical clustering, where smaller halos continuously smash together and merge to form larger ones. You would expect such a random, violent construction history to produce a wild variety of final forms. a universe of uniquely shaped dark matter spheres. Yet the result is always the same elegant density profile. It is as if an unseen law of physics acts as a cosmic contractor, ensuring that no matter how messy the construction site gets, the final invisible foundation is always built to the exact same specifications. This remarkable uniformity is a powerful clue, pointing directly to the fundamental nature of dark matter itself. It suggests that dark matter is a type of particle that interacts primarily through gravity, without the complex interactions that ordinary matter experiences. This simplicity allows the relentless pull of gravity and the expansion of the universe to sculpt all halos into the same basic shape. This shared hidden foundation has direct and visible consequences. It is the reason why the rotation curves of spiral galaxies are so uniformly flat, as the specific density profile of the dark matter halo provides the perfect gravitational grip to spin the outer stars at high speed. It governs the stability of the entire galactic disk, setting the stage for the formation of spiral arms and bars. This is the deepest structural link of all. While we see a stunning diversity in the visible beauty of spiral galaxies, with their varying numbers of arms and brilliant clusters, they are all, without exception, rooted in an identical hidden scaffold. The universe, it seems, has only one way to build the dark matter cradle for a spiral galaxy. Unlocking why this is true may finally reveal the identity of dark matter and show us the fundamental rules that dictated how everything, including our own Milky Way, found its place in the cosmos. Even the brightness of spiral galaxies follows a universal law. Across the vast expanse of space, from our local galactic neighborhood to the farthest reaches we can observe, the number of spiral galaxies at each level of luminosity is not random. It adheres to a precise, predictable curve known as the Luminosity Function. This is a cosmic census of light, and its shape is hauntingly familiar no matter where we look. The universe does not produce a chaotic mix of bright and dim galaxies. Instead, there are always many more faint, dwarf spirals than there are brilliant, giant ones, following a specific mathematical relationship that repeats itself in every large volume of the cosmos. This pattern is a direct reflection of a deeper, hidden architecture. The luminosity function mirrors the mass function of the dark matter halos themselves. Just as there are many more small pebbles than massive boulders in a riverbed, the cosmic web produces a vast number of low-mass dark matter halos, and only a few truly colossal ones. The spiral galaxies that form within these halos then paint this underlying mass distribution with starlight. The efficiency with which a halo converts its gas into stars is also a remarkably consistent process, governed by the universal physics of cooling, collapse, and feedback. This means that a dark matter halo of a given mass will, on average, produce a spiral galaxy of a corresponding brightness anywhere in the universe. This reproducibility is what makes the luminosity function such a powerful tool for astronomers. By measuring this distribution in light coming from different cosmic epochs, we can effectively watch the evolution of the entire spiral galaxy population over billions of years. We can see if the ratio of small spirals to large ones changes with time, testing our theories of how these structures assemble and fade. The profound connection is that every spiral galaxy, from the faintest smudge of light to the most magnificent whirlpool, is part of this grand statistical order. Their individual stories of birth and evolution are unique, but their collective existence is governed by a single, overarching rule. This large-scale pattern is a hidden order, a cosmic law of abundance that dictates the brightness and distribution of spirals across the entire observable universe, linking them all through a shared statistical destiny written into the fabric of reality itself. A spiral galaxy's brilliant starbirth is not an endless celebration. For every wave of new stars, there is a corresponding blast of wind. These are not gentle breezes, but colossal outflows of superheated gas, racing away from the galactic disk at millions of kilometers per hour. They are a universal exhalation, a galactic wind driven by the combined fury of supernova explosions and the intense radiation pressure from massive, young stars. In galaxies with frantic rates of star formation, these winds can become so powerful they punch clear through the galaxy's own gravitational grip, hurling precious star-forming material deep into intergalactic space. This creates a profound feedback loop, a self-regulating mechanism where the very process of creating stars generates the force that can eventually shut that process down. The hidden connection lies in the stunning similarity of these winds from one spiral to the next. Despite vast differences in a galaxy's size, history, and environment, the fundamental physics of how stellar energy couples with interstellar gas operates with perfect fidelity. The way a supernova shockwave sweeps up surrounding material, or how photons from brilliant stars push on dust grains, follows the same universal rules. This is why astronomers observe galactic winds with comparable speeds, temperatures, and densities in spirals across the cosmos. They are a shared response to a universal condition: intense stellar activity. These winds are far more than just an escape valve. They are a primary delivery system. They carry the heavy elements forged in stellar cores, the iron and oxygen and carbon essential for planets and life, and blast them out of the galactic disk. This enriches the galactic halo and even pollutes the vast intergalactic medium, seeding the cosmic voids with the building blocks of future generations. The ubiquity of these outflows reveals a critical truth. No spiral galaxy is an island. Each one is in constant, dynamic conversation with its surroundings, expelling its own essence and altering the environment it shares with its neighbors. This shared mechanism of mass and energy loss intimately connects all star-forming spirals, not through direct contact, but through a common rhythm of creation and expulsion, a universal breath held in the fiery hearts of their stellar nurseries. Each star in a spiral galaxy carries a personal diary, written in the language of its elemental composition. This is the universal Age-Metallicity Relation, a simple but profound rule that connects a star's birthday to its chemical richness. The oldest stars, the faint red dwarfs and ancient yellow suns that formed billions of years ago, are made of simpler stuff, primarily hydrogen and helium with only trace amounts of heavier metals. The younger stars, like our own Sun, are comparatively wealthy, born from gas clouds already seeded with the iron, oxygen, and carbon forged in the hearts of long-dead stellar generations. This pattern is not unique to our cosmic neighborhood. As we peer into other spiral galaxies, we find the same chemical story etched into their starlight. In the grand disk of Andromeda, and in spirals so far away their light has traveled for eons, the same rule applies: older stars are metal-poor, and younger stars are metal-rich. This is the fossil record of a galaxy's life, a gradual enrichment process that unfolded over cosmic time. The first generation of stars had only the pristine elements from the Big Bang to work with. When those massive pioneers reached the end of their lives, they exploded, scattering their newly forged heavy elements into the surrounding gas. The next generation of stars then formed from this slightly enriched material, and when they died, they contributed their own metals, further enriching the cosmic reservoir. This cycle repeated over and over, with each stellar generation building upon the chemical legacy of the last. The profound connection is the consistency of this timeline from one galaxy to the next. The fact that we observe a similar age-metallicity relation in isolated spirals and those in crowded clusters tells us that the fundamental clockwork of star formation, stellar death, and gas recycling operates with the same reliable rhythm across the universe. The timescales for a galaxy to chemically enrich itself, and the efficiency with which it turns gas into stars and then disperses those elements, appear to be universal constants. This shared chemical narrative allows an astronomer to look at the stellar population of any spiral galaxy and read its history like a book. By measuring the metallicity of its stars, they can reconstruct its past star formation rate, estimate its age, and understand the major events that shaped its growth. The Age-Metallicity Relation is more than a local curiosity. It is a cosmic clock and a shared diary, linking every spiral through a common evolutionary path written in the very elements that compose their stars. This intimate connection suggests that despite their vast separations, these majestic whirlpools all experienced a similar childhood, adolescence, and maturation, following a universal script for how a galaxy grows up and writes its story in the stars. The final hidden connection may be the most profound of all. A spiral galaxy does not choose its own spin. Across the cosmos, the majestic rotations of these stellar whirlpools are not pointing in random directions. Instead, they tend to align with the invisible rivers of the cosmic web, as if each galaxy is a leaf caught in a vast, flowing current. This discovery shatters the idea of true cosmic isolation. It means the very axis around which a galaxy turns was imprinted upon it at birth, a direct inheritance from the large-scale structure of the universe itself. How does this happen? During the galaxy's formation, the collapsing cloud of gas did not exist in a featureless void. It was nestled within a specific filament of the cosmic web. The gravitational pull from the surrounding cosmic structure, the immense tidal forces from neighboring filaments and voids, exerted a gentle but persistent torque on the infant galaxy. This force set it spinning, much like twisting a knob sets a top in motion. The direction of that spin was locked in by the geometry of the cosmic environment, a permanent memory of its birthplace. The persistence of this alignment across billions of years and billions of light years tells us something fundamental. The process of how a galaxy gathers its angular momentum is not a chaotic accident, but a universal and predictable consequence of gravity acting in a universe that is inherently lumpy and structured. This hidden coordination means that if you could trace the spin axes of spiral galaxies along a single dark matter filament, you would find them curiously coordinated, like compass needles all pointing along the same invisible magnetic field. Their individual fates of rotation are woven together by the geometry of the cosmos. This cosmic alignment weaves a final, profound thread, connecting the spin of every single spiral, including our own Milky Way, directly to the grand architecture of the entire universe. Yet another invisible ledger governs the cosmic economy of a spiral galaxy. The amount of raw fuel a galaxy possesses, the atomic and molecular hydrogen that will one day become new stars, is not a matter of chance. It follows a precise cosmic budget, a scaling law that connects a galaxy's gas fraction directly to its stellar mass and overall shape. From a small, gas-drenched dwarf spiral to a colossal, gas-poor giant, this fundamental relationship holds true everywhere we look. A tiny spiral might have half of its mass in cold, star-forming gas, while a massive one like our Milky Way holds on to only a few percent. This is not a random distribution. It is a universal trend that reveals a hidden regulatory system at work. The processes of gas accretion, consumption, and loss are governed by the same rules across the cosmos. A galaxy's mass acts as a primary governor for its gas supply. More massive galaxies possess a stronger gravitational pull, which allows them to draw in fresh hydrogen from the intergalactic medium. But this same powerful gravity also creates a hotter environment in their inner regions, where the frenetic motion of gas particles can prevent it from cooling efficiently to form new stars. At the same time, these giants often host more active supermassive black holes and experience more frequent supernova, whose powerful outflows can blow away their remaining gas reserves. Smaller, less massive galaxies have weaker gravity, making it harder for them to pull in new gas, but they also have a gentler internal environment where the gas they do possess can cool and form stars more readily. The universal scaling we observe is the net result of this delicate balancing act. It is as if every spiral galaxy is constantly adjusting its own gas tank, seeking an equilibrium between the incoming supply from the cosmic web and the internal demand from star formation and feedback. This hidden regulatory mechanism means that by simply knowing a galaxy's mass, astronomers can predict with remarkable accuracy how much star-forming fuel it has left. This consistency is a powerful tool, allowing us to model the life cycle of galaxies with far greater confidence, knowing that the fundamental processes of gas cycling follow a predictable pattern. The shared gas fraction scaling intimately connects all spirals through a common growth management system, a cosmic rulebook that dictates not only their present state, but also their future potential for stellar creation. Our journey through these 26 hidden connections reveals a cosmos far more unified than we ever imagined. Spiral galaxies are not isolated marvels. They are deeply interwoven through a vast tapestry of dark matter, universal physics, and a shared cosmic history. From the ghostly grip of dark matter that dictates their identical spins to the primordial magnetic fields whispering the same pattern across the void, we see a universe operating by a single, consistent set of rules. Their common chemical gradients and synchronized life cycles tell a story not of random chance, but of a common origin, a universal blueprint repeated across billions of light years. This hidden order suggests a profound truth, that every spiral galaxy is an expression of a single, underlying cosmic architecture. As our telescopes peer ever deeper into space, we will uncover even more layers of this magnificent connectivity, potentially revealing the true nature of dark matter itself or the fundamental principles that dictated the birth of all structure. Let this exploration change how you see the night sky. That faint, distant smudge of a spiral is not a lonely island universe. It is a distant relative, connected to our own Milky Way by the silent, invisible threads of a grand cosmic web. We would love to hear which of these hidden connections you find most profound. Share your thoughts in the comments below, and subscribe to continue unraveling the universe's greatest mysteries.